Okay, so today we're going to bring together a lot of the ideas we've been talking about so far in Chapter 3. We saw earlier on that a polynomial has a 0 at a number c, so we call the number c a 0, if f of c is equal to 0. So if we think about a simple example, if I take the polynomial, let's just say f of x is x squared minus 4, then we know that we can calculate f of 2. That's 2 squared minus 4, so that's 0. And so that tells us that 2 is a 0 of f. And that's all that we're talking about here. Hopefully you can see that minus 2 is also a 0 of this particular function, because if I plug in minus 2, I also get 0 out. So we want to know when a function has a 0. So suppose we have a function and we know that x minus c is a factor. Then we could use the division algorithm. If x minus c is a factor, what we're saying is that the remainder here is 0, because we're saying that f of x can be written as x minus c multiplied by, well, some other stuff. There's other stuff in there. X minus c might be a factor, but what we're saying is that remainder is 0. So if you remember the division algorithm, we're saying if x minus c is a factor, then the remainder is 0, because the function can be written like this. And if x minus c is a factor, we can calculate f of c, and f of c, just like the kind of discussion at the end of our previous lecture, is going to be, well, whatever q of c is, the number multiplying it is 0, and so we're going to say that c is a 0. Because if x minus c is a factor, if we can pull out x minus c, then obviously f of c will be 0, and that's in agreement with the idea that the remainder is 0. And so that's one way to look at when a function has a 0. Turning that idea around, if c is a 0 of f, then going back up to this idea up here again, the division algorithm says that this expression is unique. So if I tell you that c is a 0 of the function, then I'm telling you that f of c is equal to 0. And so that means if I were to divide the function from the division algorithm, if I divide the function by x minus c, what I must get is a 0 remainder, because this will be the remainder. We know that c is a 0, that tells us that f of c is 0, and then when we apply the division algorithm, we're going to end up getting this. We're forced to have the remainder of 0 by our remainder theorem. And so if I start by telling you x minus c is a factor, then I know c is a 0. If I start by telling you that c is a 0, I know then that x minus c is a factor. And this pair of observations lead to what's called the factor theorem. And the factor theorem is very straightforward. It just says that the number c is a 0 if and only if, in other words, the arrow points in both directions, x minus c is a factor. In other words, if we know c is a 0, we know x minus c is a factor. If we know x minus c is a factor, we know c is a 0. And so those two ideas are interchangeable. Let's do an example of how we can use this. So relegating our theorem to the corner over here, let's look at this polynomial, 2x cubed plus x squared minus 15x minus 18. And someone's told us that f of 3 equals 0. We could discover that by computation, right? We could plug f of 3 in. Well, we could plug 3 into f, so calculate f of 3. We're literally just calculating this number. And if you do that, and I'm not going to do it, but if you were to calculate that, you will find that, in fact, that is 0. And from the factor theorem, we know that, well, from the definition, we know that 3 is a 0. 3 is a 0. 3 is a function that makes f 0. So 3 is a 0 of f, and from the factor theorem, that tells us that x minus 3 is a factor of f. And if I know a factor of f, then I can use the techniques from the previous section to find the other factors. So putting that another way, we can set up this long division. So I can take the 2x cubed plus x squared minus 15x minus 18 and divide it by x minus 3, because x minus 3 is a factor. And if I divide it by x minus 3, I expect to get a remainder of 0, because by the remainder theorem, I divide it by a linear function, and so the remainder is going to be f of 3. And f of 3 we know is 0, and that's the remainder. So I know at the end of this calculation, I will get the remainder of 0. I'm interested in what the quotient is. So if we work that through, we take the 2x cubed, we divide it by the x, we end up with 2x squared. Multiplying 2x squared through by this thing leaves those two terms, 2x cubed, by the 6x squared, Subtracting those leaves 7x squared, and then I'm going to drop the other two terms down. And then dividing 7x squared by x, I just get 7x, so I'm going to add on 7x here. So this is 7x squared minus 21x. Now subtracting those two rows, we're left with minus 15 plus 21, because remember when I do this calculation, I'm subtracting that. So we have negative 15, subtract negative 21, that leaves 6, so we'll get 6x minus 18, because again I just dropped the 18 straight down. 6x divided by that x leaves us 6, so we put the 6 there. Multiplying that out gives us 6x minus 3/8 are 18, and oh look, the remainder is 0, which it better be, or we've made a mistake. And so what we've done is found a factorization for f of x. We know the remainder is 0, and the quotient we get from the top up here. It's 2x squared plus 7x plus 6, which factors f. F is now factored into a quadratic. This is our q of x, this is our quotient from the long division using the techniques from the previous section, and the leading term. This leading term, x minus 3, this divisor, is coming from the fact that we knew that 3 was a 0, and therefore x minus 3 is a factor, and then we can find the zeros of that polynomial, because once we've got a quadratic, we can always go ahead and find the zeros of the quadratic. We know the quadratic formula is always going to give us the zeros of the quadratic, so in this case the zeros of, and by the quadratic I'm talking about this term, I'm looking for the zeros of this now, because if I can find the zeros of this, I'm going to have the zeros of f. And so calculating that, I get minus 7 plus 1 over 4, so that's minus 6 over 4, and we're going to get minus 7 minus 1 over 4, so negative 8 over 4. Simplifying that, that's the same as negative 1.5, negative 3/2, and negative 2. And that gives us the zeros of this quadratic. So we factored this f into a linear and a quadratic term, and we've got the two zeros of the quadratics, and if they're zeros of the quadratic, by the factor theorem, we can write the quadratic itself, 2x squared plus 7x plus 6. That quadratic must equal something that involves the zeros. In other words, the factors. Because if we know that if negative 3 over 2 is a 0, then by the factor theorem, x minus negative 3 over 2, or x plus 3 over 2, is a factor. And if this is a 0, then x plus 2 must be a factor. Now just looking at that for a moment, you'll see that this can't possibly be equal. This term cannot equal this term. Begin multiplying this out, you're going to get an x times an x. Over here I have 2x squared, but this is only going to yield x squared. And so I have to put something in the front here, or else it can't possibly work. So I'm going to place that 2. We'll talk about this in a second. But the 2 in front of the x squared, I'm just going to put it there. And so if I then multiply this whole thing out, we're going to have 2 times, well, this will be x squared, although that doesn't look like an x squared. This will be 2 times x squared, and then there'll be a 3 over 2x, and then there'll be a 2x, and then there'll be a 3. And if we put all this together, we're going to have two lots of, well, I've got 3 halves here and another 4 halves there, so x squared plus 7 halves x plus 3. And if we multiplied that out, we'd come back to the original function over here. And this goes back into the function, into the polynomial. So the total factorization of f is what we're actually looking for, or the zeros of f, put another way. So we can write the factorization of f as follows, which gives us this expression. We've got the original x minus 3 and then the factorization of the polynomial. Those two things multiplied together give us the original function f. And if we combine those things, we get the total factorization of f itself. So f has these 3 factors, x minus 3, x plus 3 over 2, x plus 2. That means we can read off 3 zeros of f. The zeros of f are the numbers 3, minus 3 halves, and minus 2. So from the initial piece of information that we had, that 3 was a 0, we determined that x minus 3 was a factor, and therefore we got a quadratic. And as soon as you've got a quadratic, we can use the quadratic formula and find the zeros of that quadratic. Once we've got the zeros, we can write down the factors using the factor theorem. And so that allows us to take that back into the full factorization of f here. And remembering our original function, It was a cubic, and it started with 2x cubed. And notice how the 2 that was there, along the way, for reasons that seemed to make sense at the time, we took that 2 and we put it in front of the factorization, and then we just needed the zeros. So if I know the zeros of a polynomial, and here I go, here are the 3 zeros of this third degree polynomial, then I can write down the corresponding factors, and here are the 3 factors. And the only other element I added here was the 2, and that was the number on the leading term. That was the leading coefficient, in fact, and I wrote that out in front. And that gave us what's known as the complete factorization of f. This is the complete linear factorization of f. And in fact, we can always do that. And this is guaranteed by the complete factorization theorem. It says that any nth degree polynomial can be completely factored into n factors, and the number out the front is always going to be that leading coefficient. You can see it's right there in this general formula. And so this is exactly what we've done in this case. We have 3 zeros for this cubic polynomial. We've written down the corresponding 3 factors. We've written the leading coefficient out the front. And we've ended up with what's known as the complete factorization of this function f. So in the previous calculation, I stated at the end that the complete factorization theorem for an nth degree polynomial says that I can always factor it into n linear factors corresponding to n zeros. The zeros aren't necessarily different, but I can make n of them. They'll have multiplicity, just like in the section 3.1. It's the fundamental theorem of algebra that allows us to see that every polynomial has exactly n zeros. Now, as we can see, the fundamental theorem itself tells us that every polynomial has at least 1 zero. And that might not seem very exciting, right? Let's suppose I give you an nth degree polynomial, and this theorem says it has 1 0. Well, if it has a 0, let's call it the first 0, then if it has a 0, by the factor theorem, it has a factor corresponding to that 0. So the factor theorem says that if C1 is a 0, then x minus C1 is a factor. We can do the long division to get what's left. So this might be a, ninth degree polynomial. It's going to have a 0. The fundamental theorem of algebra says it will have at least 1 0, or it has 1 0. That means it has one factor. What's left must be a smaller degree polynomial. So in my sort of imaginary example, it would be degree 8. In general, it would be degree n minus 1. And so I've pulled off this factor corresponding to the 0, and I've got some polynomial left. The remainder must be 0, precisely because C1 is a 0. All right? Well, that's good, but we can continue down this road because Q itself is a polynomial, and it's got a degree bigger than 0, and that means Q has a factor. So let's call it C2. So I can factor Q, but hang on, Q is a part of F, so I can kind of introduce those two factors, and Q itself must get a quotient once I introduce that. Q has a 0, so there's the corresponding factor. Divide that out, I've got a quotient. Okay, but now I've got another polynomial, and so I can take that polynomial C2, it must have a 0, sorry, Q2, it must have a 0, and so if it has a 0, I can factor it and pull out the factor corresponding to that 0, let's say it was C3, and that will generate some other quotient hanging off the end here, and I can keep going until what's left here is actually linear. At some point it'll be linear, it'll be a first degree polynomial, and what I've pulled out are n factors. If I start with a cubic, I'll do it 3 times, I'll end up with 3 linear factors. And so, although the fundamental theorem of algebra says every polynomial has at least 1 0, together with the factor theorem, we can use it to show that every polynomial actually has exactly n zeros. So as a result of the fundamental theorem of algebra, a degree n polynomial has precisely n zeros, always. The one tricky complication here is they may not be real. They could be real or they could be complex. So we'll talk about that in the next lecture, the idea of generalizing this to allow for complex zeros. So in this final example, we're given a 4th degree polynomial and we want to find the complete linear factorization of that polynomial. And we're also given 2 of the zeros of the polynomial. And if we know zeros, then we know factors. Namely, x minus the zeros. So in this case, x minus the square root of 5 and x minus the negative square root of 5. Those are both factors. And another way of writing the second one is just x plus the square root of 5. So we have 2 factors, And if we have two factors, then we could divide them out of that fourth degree polynomial and see what's left. But I don't really want to do the division with the square root of 5 there. So let's use an idea to get rid of the square roots of 5. If we multiply those two factors together, we still have a factor of f. If each of these is individually a factor of f, then their product of them must still be a factor of f. And so if we multiply this out, and you might want to pause the video right now and do this calculation, but if you multiply these out, you should find that you get x squared minus the square root of 5. And so that is also a factor of f. Well, a factor of f. And since we have this factor of f, we can divide f by it, and we've got a second degree polynomial here, and if we divide the fourth degree by it, we'll end up with another second degree. So let's see how that works. So we'll just do the long division from the previous section, and I've written our function f in here, and the thing we're dividing by is x squared minus 5, but there's a 0x in there, so I wrote it in there just to keep the columns even. So if I take 3x to the 4 divided by x squared, I get 3x squared. That's the first term in our quotient, and multiplying that back out gives 3x to the 4, and then we're going to have no x cubes, and minus 15x squared. So subtracting those two terms, that's a squared, subtracting those two terms, the 3x to the 4's cancel. We're going to be left with a single x cubed here. And I know this is hard to read, so let me go back to the other color. This is going to be x cubed. We're subtracting minus 15 from minus 17, so we'll be left with minus 2x squared. And then we're just going to drop those two terms down, minus 5x plus 10. And then continuing in the same manner, x cubed divided by x squared, that's a single x term. Multiplying that out will give us an x cubed plus, again, no x squareds and minus 5x. And when we subtract those two terms, we're going to find that the x cubes cancel and the minus 5x cancel. And what we're left with is minus 2x squared plus 10. Just dropping that 10 down. And we can continue again. This is a second degree polynomial. We're dividing by a second degree polynomial. So we have to have a remainder that's less than second degree. So we can keep going. We take minus 2x squared divided by x squared, we get minus 2. Multiplying that out, we get minus 2x squared, this time plus 10. Those two things cancel. They have to cancel because we know that this thing here is a factor. And if it's a factor, then the remainder must be 0. So what we're able to do now is express f in terms of two polynomials, which are coming from the factor that we know, x squared minus 5, which comes from the two individual linear factors, and the quotient that we just found, 3x squared plus x minus 2, which is this quadratic. And if we've got a quadratic, we can find the zeros of that quadratic. And the zeros of this quadratic will be the zeros of f, because these are all multiplied together. And the good thing about being left with a quadratic up here is that once we have a quadratic, then we can always just use the quadratic formula to find the zeros. And doing this calculation, this is minus 1 plus or minus, you'll see in the square root here, the discriminant is 25, so we've got plus or minus 5 over 6 in the denominator. So this is minus 6 over 6, and the other one would be 4 over 6. So our two zeros are minus 1 and 2/3. And they're zeros of the function f, precisely because they're zeros of this quadratic. And so we've got the zeros of f. What were the zeros of f? Well, the zeros of f were given to us, two of them, plus the square root of 5, minus the square root of 5. We've just found two more, minus 1, 2/3. We know from the fundamental theorem of the fundamental theorem of algebra, that every polynomial, an nth degree polynomial, has n zeros. And so now we know we have all the zeros. And so each zero corresponds to a single factor. Some of the factors might be the same if the zeros were the same. But in this case, we've got a whole bunch of different zeros. So we get a whole bunch of different factors. And there's our complete linear factorization. But there's clearly something missing. The complete factorization theorem tells us that the leading coefficient always appears at the front, because otherwise we wouldn't be able to get the right our polynomial when we expanded it out, because just multiplying these terms together would give us x to the power of 4, and our polynomial started being 3x to the power of 4. So here's the complete linear factorization of our polynomial f, which corresponds to the 4 zeros that we found. And you've seen how complete factorization works with polynomials, so have a go at the pre-class work, and we'll talk more about this soon.